Hi there. Now that we've learned about the DNA sequencing reaction, we'll see about the other considerations that are needed to use that reaction in order to sequence genome. In this video, we'll specifically focus on issues of data quality, we'll talk about sequencing strategies, and then we'll talk about, once you've done the sequencing, sequence assembly, and the problem of repeat regions and how you get around those. So here we see the sequencing output that you got, this time from a capillary sequencer. The lanes are all straight and no smiling is going on. And then we're going to look at a single one of these lanes and record the fluorescence intensities that we read, and then we're going to read out the sequence, and we'll blow up a region on the next slide. And here you can see high quality sequence. It's easy from your eye to see which is the predominant color and therefore read out the bases. And you see here there's 4 T's in a row, simple to see. And you can see that in some places some of the background fluorescence from the other bases starts to be substantial. And on this slide we see an example of a sequencing trace that has seriously degraded in quality. Right now we're up around 800 base pairs or so in a read, and in general sometimes you could get a little larger, but gels can only do single base pair resolution out to about 1,000 bases. And at this point you have problems of overlap, of high background fluorescence, weak intensities in general, and at this stage it's almost impossible to call out a sequence based on these fluorescence traces. Now, one of the clever things that was done in interpreting this data is that each base call was assigned a quality score, and from that quality score you could derive a probability on how likely that call is to be correct. So then when you're assembling the sequence or putting it all together, you know which sequences you can trust very highly and which ones would be more problematic. If we talk about other things besides just a decrease in base pair resolution, what is causing some of these issues? Well, you always have some non-specific, relatively low-level binding of the primer of the DNA, and so you'll have different reads, and that contributes to the background. DNA secondary structures, if you achieve a cloverleaf or a hairpin, that's going to affect the migration speed, and so that's going to affect whether an N+1 sequence comes right after an N sequence of DNA base pairs. And also, since the bases are different and that their fluorescent molecules are different, they had different efficiencies of incorporating into the polymerase. Again, these are non-natural nucleotides, and this can all contribute to degradation of the observed signal. So in dealing with those and in sequencing the genome, here are the steps that were required for sequencing genomes in the 1990s and early 2000s. The first thing you had to do is select a strategy, and we'll say more about in the next slide. You would get the DNA from a source, and then you would chop it up and into small pieces and take that DNA, put it into, create a library of small DNA pieces, package that DNA into plasmids. All of those plasmids have to be stored. Then when it comes time for sequencing, we're going to have to prepare DNA from each of those plasmid and do mini preps of the DNA. And then we'll do the sequencing reaction. Then we'll read out the bases and assess the quality. And then we're going to put those puzzle pieces together, the sequence reads together into long stretches of contigs. And then finally, at the very end, we're going to annotate those sequence and identify where the genes are. So when the human genome was sequenced in 2001, 2 groups contributed to it. First was the public group of NIH, led by Francis Collins and Eric Lander playing key roles. And there was also a private company, Celera, which was headed by J. Craig Venter, and they sequenced the genome also. These 2 groups used very different strategies, and both were quite useful in producing the final sequence. It's probably fair to say that without the public effort doing their strategy, Craig Venter and Celera would not have been able to assemble a genome by themselves. On the other hand, it's probably safe to say that Solaris sped up the public effort by maybe 5 or 10 years by putting this intense pressure on, not wanting to lose to a company the human genome, and so that really sped up the NIH-funded effort. And so as a result of both groups working, we had a high-quality sequence many years earlier than was predicted. So to describe the two different strategies, we'll use the analogy of a set of encyclopedias and the informations contained there. You may have heard from your grandparents that encyclopedias used to be books, many volumes, which information was arranged alphabetically. Anyway, the public effort took one volume of the encyclopedia at a time. They would split it up into small pieces of DNA, sequence those, assemble those, and then they would take the information from a second volume, also do the assembly, and build up the sequence over time, but spent a lot of effort dividing the DNA into volumes and doing these extra reads. This was definitely very time-consuming. It was definitely a more expensive task because of all the labor. However, it was easier to assemble the sequence than at the end because you were only trying to assemble sequence from one volume at a time. Solaris took the approach that we're not going to look at any of the volumes. We'll just take all the DNA, sequence it many, many times faster without keeping track of which plasmid is from which volume. And this is certainly quicker and cheaper. Now, there's always been a question about whether they could have assembled this final sequence entirely on their own. However, they had access to interim data from the public effort, so it's unclear. It's basically neither here nor there now. And again, they deserve a lot of credit for eliminating a lot of time-consuming steps, and it's part of the reason sequencing can go as fast as it can now. There are other reasons for that as well. We'll see that in the next video. So just to make very clear, this fragmentation system, where you have the entire genomic DNA, it's going to get fragmented into lots of different pieces. Each of those pieces is going to be cloned in a plasmid. Each of those plasmids is going to be put into bacteria. The bacteria are going to grow up on plates and colonies, and then we're going to isolate the DNA from each of these bacteria and sequence them using the sequencing reaction, which you already know about. But since sequencing was very expensive at that time, you didn't want to sequence every single plasmid that you got from fragmentation, because there was a great deal of overlap between the sequences on each plasmid. So what they attempted to do was create a minimal tiling path with sequences from different plasmids, and only sequence the ones that were boxed in red here. So the question is, how did they order these plasmids, and how did they realize which sequences overlapped by small bits so that you could continue to read a sequence starting here and then jump to this one and continue? So the way the plasmids were ordered was using restriction enzymes to cut the plasmids and produce fragments of certain lengths that then could be compared amongst the plasmids. Those are different lengths. When you saw fragments that were held in common here from the first two plasmids, that you could see those overlapped, and so that you could realize that this plasmid and that plasmid overlapped by a few fragments. You could also determine that these other three plasmids were completely redundant with these two, so you wouldn't need to sequence these other three. Now, it was still a pretty Herculean effort, taking each plasmid, cutting it with a restriction enzyme, running them out on gels, and identifying with high accuracy these fragments that were the same size to build the overlap, but nevertheless it was a technical feat that was achieved. And I think you can see right away why if you didn't have to do these steps and just could go to whole genome shotgun sequencing, that there would be certain advantages in speed and expense. And when we think about the shotgun methods, all this is called the mapping phase. This is the ordering of the physical library of the plasmids, making sure they overlap. And one of the things that Celera did, which is very clever, and we'll see why, is when they were cloning fragments of the genome, they put them into plasmids of different sizes, or they took inserts of different sizes. They had most of the sequences, probably about 70% of the sequences were 2 kilobases long. But there was also 10 kilobases, 50 kilobases, and a few very large inserts of 150 kilobases, building the genomic library. A second thing that they did is they sequenced these inserts from both ends, and we'll see what that means. These were called paired end reads. And using the distance that between the two ends is a critical piece of information used to calculate the sequence assembly. The other thing that was done is because it was cheaper and easier to do the sequencing and faster, that they were able to get higher fold coverage of the genome by sequencing more plasmids. Of course, 5-fold was considered pretty good back then, and now with next generation sequencing, you'll typically achieve 40-fold coverage of a genome. And I'll also say that it's since we have a draft sequence of a human genome, what's done now is sometimes referred to as resequencing, and it's much easier to assemble a sequence when you know what you're trying to achieve based on the reference sequence. So now that we've done a lot of sequence reads, which is represented by each of these little arrows, we're going to try to assemble a sequence into contigs, and contigs are simply referred to as contiguous base pairs without any gaps achieved from overlapping reads. So in here, it's probably about a dozen or so reads are forming this single contig here, if each of these reads are about 1,000 base pairs, this contig might be 4,000 or 5,000 base pairs. And the way the sequence is assembled is very much like the way that the physical library of plasmids was overlapped. Remember there we overlapped restriction fragment lengths. Here we're going to take the sequence fragments and we're going to find sequences that are in common, GTTCA, GTTCA, and then we'll know that this comes from the same region, and so that we can create a consensus sequence starting here, ending here, represented here. And it's because you have random shearing of the genomic DNA that you get these overlaps, which are useful for a sequence assembly. But when you're overlapping the sequences, you run into trouble with repetitive DNA. As you might recall, over 50% of the genome is repetitive DNA sequences. So if you have repeats, DNA repeats here, one of these sequences, GATT, is at the very end over here, and here you see GATT again. Well, you might just accidentally overlap that, put that right on top of each other. I don't know why it wasn't shifted over here 4 or 5 bases, but then you would be reading along here, and then you would continue on here in your overlap, and you might miss this entire region here in the center. So the question is, how do you not get fooled by the repeat sequences to assembling something that in actual fact is not next to each other? And this is where the different fragment sizes comes into play, and the fact that you're going to do paired end reads, so it means sequencing it from both ends. So let's look at two of the sizes, 2 kilobases and 150 kilobases. Here we have a cloned fragment, we know, and we're going to sequence on both ends. We know that when we sequence these two and we put them together, that this portion and that portion is going to be approximately 2,000 bases. You don't know that to base pair resolution, but it's approximate. Whereas if you have some fragments that are 150 kilobases, you know when you sequence this side and you sequence this side of the plasmid, you're going to have these two separated by about 150 kilobases. Now you can't sequence any of this interior region because you don't have primers. Again, the primers, which you know the sequence, are right here in the plasmid, and that lets you sequence in on the end of the plasmid. You don't know ahead of time what the sequence is, so you can't have any primers that are going to sit down here and sequence. But let's look at the consequences of knowing that this read and that read is 150 kilobases away. So let's say one of the reads is here in a repetitive region, and the other bases, maybe the 2 kilobases, will be right over here, and not to scale, 150 kilobases is over here. So then as you start to assemble this sequence or this sequence, and you know that these two are linked, then when I find the piece that goes here, I'm going to have on the other end the piece that goes here. So by working on one end, you're able to position correctly or anticipate that there is repetitive sequence here and not get fooled. Now the reason for having different sizes is you could get unlucky, and maybe this would be an example of a 10 kilobase piece, that you could have one sequencing end in here and one sequencing end in here, and you're not able to anchor these reads in any way with unique sequence because they're both awash in repetitive DNA. So by having this distribution of different sizes, you could, with high enough reliability, get one end. If it was caught in the repetitive region, the other end would be in a non-repetitive region, and from that you could deduce the relative locations in the repetitive DNA section and get an idea for how big these repetitive sequences are. These paired end reads could also be used to bridge contigs. If you have a lot of sequencing and then a gap, if you have one plasmid that showed the had similarity to one end of one contig and one from another, you would immediately have an estimate for how big the gap is separating those two regions. And sometimes they were very large, so the big plasmids were quite helpful. Once you also knew about how big a gap was, there are brute force methods of finishing it. You could put a primer down here where you knew it and sequence 500 base pairs in. Then you could create a new primer and sequence 500 base pairs in. Create a third primer and again sequence. And this was called primer walking, and this is one way of closing gaps. Ultimately what you want to produce is a high quality contiguous finished sequence. And in truth, that is still not completely completed for the human genome. For instance, we do not have good sequence in the centromeric regions of chromosomes. At the time in 2001 when we declared that the human genome sequence was finished, it was approximately 93% sequenced. And accuracies were around 99.99%, I believe. At the time the genome was sequenced in 2001, only about 93% of the sequence had been completed, and I believe the accuracy at that point was around 99.9%, which sounds very good, but when you have 3 billion base pairs, that means there's approximately 3 million errors. So DNA sequencing on the scale of a eukaryotic genome demands highly accurate information. It's one of the reasons you sequence every sequence many times where you have a high fold coverage. Okay, so that's a basic overview of genome sequencing. Thank you for listening.